Okay, so welcome to the second session of the conference, and we're very happy that Larisa Jonke will tell us something about adiabatically-induced Kawaguchi geometry.
Thank you, David, and thanks to all the organizers. I'm very happy to be again in Wrocław. My first time was actually 10 years ago on one of these Max Born symposium. I have very fond memories. I was invited by Professor Lukierski, and it was also part of one cost action meeting at QSpace at that time. So I'm very happy to be here. And I'm also very happy because this Max Born Symposia had very long history, and there were many meetings, and they kind of made Wrocław theoretical divisions in particular on the map, and they are overlapping with this new series of events, with new community dealing with integrability, dualities, and deformation. I was kind of invited on the sort of zeroth meeting, which unfortunately was canceled due to COVID. So it turned out in the very nice series of online seminars. So again, thank you all. And I hope you will find this topic and the talk interesting, because it is slightly off topic, but usually here in this community, I would present some of my work on non-commutative deformation or dualities, but this is something new we are working on, and I'm very excited about it. So I decided to present this. So it's a bit cryptic maybe for some of you. So adiabatically-induced Kawaguchi geometry and jerk in quantum classical system. So roughly, I will explain some of the more details, but roughly what we want to do is to start with some quantum classical system, think molecular dynamics, Ehrenfest dynamics. So I have classical nuclei and then dynamics of the quantum electrons. What we want to do is to integrate out the electronic quantum degrees of freedom to obtain effective action and equation of motion for the classical motion of nuclei using adiabatic approximation. And what is interesting in all of this procedure is that along the way we kind of discovered how a new type of geometry, which we didn't know about before, appears there in the effective equation, and how third time derivative of position, which is jerk, appear in what happens to be non-Newtonian equations of motion. So this is kind of outline of the talk. I will say some generalities about how we do this how we find this effective action and effective equation of motion in adiabatic approximation, tell you something about different geometry, quantum geometry, which you standardly find in this system, and then how our effective system in the end displays Kawaguchi geometry and what are the consequences of this. So let me say, just to introduce and motivate and kind of make you think of a connection on the things you know, one thing we had in mind here, although it says quantum classical, usually quantum in fast degrees of freedom, and classical in this sense nuclei would be very heavy and slow. So it's not kind of decoupling we had in mind. We have kind of separation between slow and fast dynamics. And the classical example you all know is Foucault pendulum, for example, where you have the moving of the pendulum plane due to very weak and in the end slow degrees of freedom due to the Coriolis force. It moves around the circle. The plane moves around the circle. What the system we are looking at, usually, you know, I mean, it's a Newton law. You know how to integrate directly, either analytically, if the system is integrable, or you can just do it numerically. However, this is usually very costly, because if you have fast degrees of freedom, you have integrate over a very long time and many oscillations. So it's computationally very costly. Also, it doesn't tell you much. It doesn't really tell you what is this, doesn't explain what is this slow dynamics you see effectively in your real physical system. So what we want to do, as I said, we want to eliminate the fast variables and obtain effective equation of motion for the slow one. Okay. Often in this kind of system, you find that this effective description have a very nice geometric interpretation. So in the Foucault pendulum, basically, what you obtain for the slow degrees of freedom is just a parallel transfer on the sphere. I mean, you're just measuring the curvature. You're going around, you're doing parallel transfer of the sphere. In molecular dynamics, this is known to mostly due to Berry and his discovery on the Berry phase. Basically, the molecular nuclide would feel a gauge potential known in the solid state as Berry-Mead-Truller gauge potential, and the quantum state, adiabatic state, would acquire the well-known Berry phase. What we have seen so far, and what is understood so far, is that in the low order of adiabatic approximation, geometry is well understood. What hasn't been done is higher orders approximation. They were done in very specific cases and not systematically, and it's mostly unexplored. What we wanted to do here is to go to the third order, describe what is the geometric structure induced in the third order of effective adiabatic approximation. And the reason we want to do it, I mean, physical reason why we want to do it, is that we want to use geometry to somehow improve efficiency in calculation of the higher order corrections, which are physically relevant in experimental and material science. We want to improve efficiency in two-way, kind of. It turns out that this adiabatic approximation is very good in the sense that you will have a parameter that controls the accuracy of your approximation, which is extremely important to know the accuracy of your approximation. And also, of course, we want to use geometry to kind of make calculation more efficient. Okay. Go. So this is the quick summary of the talk and the results. So just remember this and then you can go to sleep. So we will start with the mixed quantum classical system, having in mind quantum electrons and the nuclear. We will adiabatically eliminate the quantum part regarding to the electrons to get effective equation, action and the equation of motion for nuclear. And we will do it in order by order in a parameter epsilon, which will be explained in the next slide. And what do we obtain? So what is well known in zeroth order, the effective force is standard Bohr-Oppenheimer force given by the derivative of the eigenvalue of the adiabatic state, energy of the eigenvalue of the adiabatic state. And this is just gives you just the potential on the manifold M, which is parameterized by the nuclear coordinates. In the first order, you get, this is also very well known, Berry-Lorentz force. And on geometric side, it means you had a gauge, you induced a gauge field, a mu. On the second order of epsilon, you get the first non-adiabatic correction to your system. And it turns out that effective force is the same as the first order. It's just the mass matrix of the nuclear get renormalized. And then, your induced geometry is still Riemann geometry in this level. what is new and what is we obtain here is that in cubic order, the equation is non-Newtonian. You get dependence of the equation on the third derivative of the position, nuclear position, and the induced geometry in that in this instance will be described by Kawaguchi geometry. Sorry.
Is this connected to like a background field? And is the elimination of quantum like connected to RG protocol?
I'm just going there.
Okay.
Yeah, sorry. So no, it's just introduction and overview. Okay, let's see. So this is the action we start from. So the first part is the classical part that describes nuclei, which are parameterized by their position depending on time. Dot derivative are the velocity, and this is mass matrix. And obviously, in this sense, you can see that in the classical part, this is standard kinetic energy, but basically, this is a bare mass tensor, and it induces standard Riemannian metric on the manifold spanned by the coordinates of the nuclei. And this is standard standard electron part of the action. You just look at the Euler-Lagrange equation, which are defining the RFS molecular dynamics. You have the standard Newton equation for the nuclei, which is forced by the force coming from the Hamiltonian, describing the electronic state. Note that we our main parameter here, parameterize everything is in time, so we assume that we have time dependence in the Hamiltonian due to the time dependence of the position of the nuclear degrees of freedom. So you have a forced Newtonian equation for the nuclei. Note that acceleration, this acceleration is defined like this. This is the covariant second derivative, where the connection is defined with respect to this bare mass matrix, which we interpret here as a metric on the space. What we want to do here is to integrate out the electronic degrees of freedom and get effective equation for the slow varying nuclear degrees of freedom. Note, okay, I just want to say here, there are two ways of doing this. You can expand slowly, slow varying the equation of for the electrons and just try to get effective equation of motion without the action. Or you can do it in the action. We did both. What I'm presenting here will be done first deriving effective action and then equation of motion coming from there. These two things do not overlap. There is a difference. Equation of motion coming from these two approaches do not overlap. There is a small difference, which I don't think I will have time to discuss here. Okay, so how we integrate out the effective, how we integrate out the electronic degrees of freedom and what is really adiabatic perturbation theory. So what we need, as I said in the beginning, it's not perturbative expansion in a weak coupling, although it is assumed that because of the slowness, the coupling is weak. However, the key element is that we have slow and heavy degrees of freedom, and how we control the adiabatic approximation. Well, adiabatic approximation just means that your fast degrees of freedom instantaneously respond to the changes of the slow variables. That's just the term. So to have these, you introduce the adiabatic parameter epsilon, which will control your approximation. And then you scale, your approximate solution is of pth order is given like this. So the difference of approximation to the exact state goes to 0 in this limit. How you obtain this? Basically, you have to scale the mass tensor with adiabatic parameter and introduce something called slow time, where you rescale your time parameter with this adiabatic parameter epsilon. What happens in your equation of motion is that your Newtonian part for the nuclei stay the same, doesn't the dependence of epsilon cancel, but you get a singularly perturbed Schrödinger equation for electrons. And this is how you kind of do the approximation. So you expand this equation in the powers of epsilon. Okay. So, as I said, zeroth order is very well known due to Sir Michael Berry and his seminal work from '84. So, zeroth order solution, basically, your physical system, your Hamiltonian, is in an eigenstate, in a adiabatic eigenstate n with energy En of x, which depends on time through the dependence on the position. And your wave function is basically your adiabatic state. And with a two-phase factor. One phase factor is dynamical and basically is given by the exponent of this integral of the energy. The second phase factor is geometric. And this is this geometric Berry phase introduced by Berry in his work. It's given here. And then, as I said, you have in this approximation appearance of the connection on the principal circle bundle over the M, which induces the Berry curvature or field strength of this connection. And what's important for our construction also, it gives you, this connection gives you splitting of your bundle into horizontal and vertical parts, where the horizontal parts define these gauge covariant derivatives. Just a reminder, so our physical states, so electronic states, live in a ray space. Your Hilbert space is a projective space where you have defined on this space, you have a metric, which is in a solid state community called quantum metric. It's a gauge covariance, it's a measure of the distance on your Hilbert space, where this is a Hermitian metric. So real part is standard Riemannian metric, while the imaginary part is coming from the Berry curvature. And on your space of states in our system, this is actually, this metric is a pullback of the Kähler metric that is canonical, that canonically exists on this Hilbert space. However, note, and in our construction it's never, generally not, this metric is not Kähler. It would be Kähler if I have the same dimension of the Hilbert space of states and the parameter space of nuclear, but this I never assume, so it will not be Kähler. But so this is the structure that's canonically there, it's Kähler, but in our system, this pullback metric is not necessarily Kähler. Okay. So I told you that what we want to do is to find the effective electronic Hamiltonians that will help us determine the effective action for the nuclei. And you can construct this effective Hamiltonian order by order in adiabatic parameter epsilon. by applying series of unitary transformation. The zeroth order transformation is basically you just diagonalize your Hamiltonian and go into instantaneous adiabatic eigenstates. You just diagonalize your metric, and then you apply this series of unitary transformation on this Hamiltonian order by order in epsilon. Which these transformations are given here, so they are connected to unity. G's are the generators of the transformation. How do you determine these generators? You fix them by requiring that in given order of approximation, your Hamiltonian is diagonal, and you push the off-diagonal elements to the second order. This is how you choose these G's. This is the role of them. So that you get, in each order, these effective Hamiltonians become exactly diagonal. Off-diagonal elements go in the second order. This is how you do your approximation. So in the zeroth order, we just get this diagonal Hamiltonian, which has eigenvalues, energy eigenvalues given by the adiabatic state. In the first order, the effective Hamiltonian, apart from the energy, will get corrected by this contribution coming from the gauge potential. In the first order, you will get additional term, which, if you remember my quick summary in the beginning, so it will correct actually the mass matrix or a metric, if you want, Riemannian metric on your nuclear manifold by this factor. And what's most interesting part, in the cubic order, you will get a new correction. You will get effective Hamiltonian that depends on acceleration, not only on the velocity anymore, now on acceleration. This is just what we obtain. So what we've seen here, so this is the, as I told you in the beginning, gauge potential, renormalization of the mass or the metric, and then this new structure appearing in the cubic order. You evaluate this from the approximation you did, you extract what is this mass correction coming from your states of the system, and this is resolvent given here. So this is your mass correction, and then in third order you get two expressions. Omega is not named omega for no reason. This is actually almost symplectic structure, almost because not imaginary part. So this thing is skew symmetric in mu and nu. When you make a when you exchange mu and nu, this is just a complex conjugation. So this is antisymmetric in mu and nu. Real part of this expression is always symmetric because there is no change of the sign when you do the conjugation. So this is skew symmetric. However, in our system, it's almost symplectic in the sense it's not closed. D of omega is not zero. So, and we assume it's invertible because we assume that in our approximation, the energy level will not cross. Otherwise, you have to be more careful. You can still do the thing, but it requires more job. And then we get fully symmetric expression given here, which is not a tensor under the change of the coordinate system. It transforms, basically, it transforms like a connection, which we will see in a moment. So these are kind of our new geometric ingredients in the effective, appearing in the effective Hamiltonian for the electronic degrees of freedom. And now we want to evaluate the, once we have effective Hamiltonian, we want to get the effective equation of motion. So we will use the effective Hamiltonian to write the effective action for this part of the system. And then we will get, with its standard variational principle, we will get equation of motion in each order. So in the first order, our effective action, if you remember, there was zeroth order energy, and then in the first order in epsilon, we had this gauge potential appearing. It's a gauge potential in the action. It is gauge invariant because I assume that the total derivative in time will vanish. So I apply the boundary condition. So this is, for this system, this is gauge invariant expression, although I have a naked gauge potential. And your Euler-Lagrange equation for the effective motion of the nuclear is given here. So you get this, what I said in the beginning, Bohr-Oppenheimer horse coming from the zeroth order. And in the first order, you get Berry-Lorentz from the field strength of the gauge potential. This denotes that acceleration, which is covariant expression, it's given in terms of the, it's constructed using the connection coming from this mass matrix interpreted as, taken as a Riemannian metric. So this is just, so here in acceleration, I have a Levi-Civita connection for this invariant metric. Okay, in second order, as I already hinted, you get additional term in your effective action, which I show how it looks in our physical state, in the terms of the physical states in integrated out, and this just renormalizes your mass matrix or your Riemannian metric on the parameter space, and your equation, effective equation of motion, is still Newtonian, looks like the one in the previous order, with renormalized metric. And then, you know, you get also now in the acceleration vector, you have a Levi-Civita connection with respect to this metric. And this, up to now, this was used, this was known and used. This is nothing really new. What we found in the third order is actually new. So I show you, this is the coming from the effective potential, this correction to the effective action. Note that action depends explicitly on the acceleration vector. It has these two functions which we defined, which we obtained through the approximation, and this is the form. Obviously, I know how to do Euler-Lagrange equation, but because of the acceleration, I will have third order derivative with respect to time in the equation of motion. It will not be Newtonian. This is just the, know that, you know, this higher time derivative also in the action and in the effective equation of motion have been considered in different real-world problems, starting from the biological and biotechnological system when you want to describe the movement either of robotic arm or the real human arm in the real life setting. You have to take into account the change in the acceleration and sometimes also the higher correction, but this really plays a role also in the different system. Okay, but let's stay with this. So we just computed what is the equation of motion in the third order. So cubic corrections come with omega and psi, and zeta and psi, and then this is the quadratic part. You see the up to quadratic correction, we have all the nice geometric definition, but here we are bit at lost. We got some two functions which are not a tensor and which don't transform as a tensorial quantities. And we want to understand, first of all, what is the geometry underlying the action and what is the covariant kind of definition of these, because then we have better control over the whole thing. And to explain you the geometrical content, I will have to tell you something about this Kawaguchi geometry we stumble upon in this problem. But to start with, something which might be more familiar to you, let's think about Finsler geometry. And unlike the standard law that says, let's think about Finsler as generalization of Riemann, it's like something beyond Riemann, Chen said, well, no, let's think of Riemann geometry as a special case of Finsler, the one without quadratic restriction. Let me tell you what this means. So Finsler geometry is defined on the smooth manifold M with the Finsler structure defined as a map from the tangent bundle to the positive real line. And these functions satisfy homogeneity property. Note here x is the coordinate on the smooth manifold, y is the coordinate on the fiber. So in our case, this would be velocity vector, for example. So Finsler functions satisfy homogeneity property, and the Hessian is strictly positive. And the quadratic restriction, that this is just, Finsler, I think this is positive, and you take out the 0. So what is quadratic restriction? If you restrict Hessian to depend only on x, not on y, so this derivative should depend only on x, you just get Riemann. So in this sense, if you relax this condition, you get Finsler. So it's a Riemann without quadratic constraint, without imposing that what in Riemann becomes metric with the constraint depends only on the position. It can also depend on the direction, on the velocity. So, but with this, as I told you, this is, think here, manifold coordinate tangent bundle for us velocity. So to get a structure that depends also on acceleration, well, we need one more step. And this next step is kind of obvious. What you need is to go to the second order tangent bundle. You just need to introduce the extra coordinate that would correspond to the acceleration in the problem. So Kawaguchi geometry works for any tangent bundle. We are staying to the second order tangent bundle just because our problem up to third order goes only to the acceleration. And this is known from the work of Kawaguchi in 1936, 38. You can define this Kawaguchi structure function to obey homogeneity condition like this, which is designed so that your arc length stays reparameterization invariant. So you define this function k with this condition such that this thing is reparameterization invariant. In this second order, it was already basically studied by Elie Cartan even before Kawaguchi discussed the whole general structure. And now we have to find the specific geometry within this setting, which would correspond to our physical problem. And it turns out that kind of starting from what we've seen for Finsler, that you have to define these structures on the coming from your Kawaguchi function in such a way to obtain our system. So we defined the geometry on our problem as that third derivative, that second derivative of the cubic function gives us the omega, which depends only on x. So think of quadratic constraints for the Riemann. So the cubic derivative of k, cubic k, would again depend only on x. And we don't have any other function, so this is kind of singular. This we need to stay in the third order equation of motion. This is our physical, this is not part of geometrical data. For us, omega, non-degeneracy of omega is our assumption, basically, to be able to solve some things. And this condition basically tells you that with homogeneity properties, omega is a two-form, non-degenerate two-form, and gamma is some symmetric function that transform the way we've seen before. And this special case of Kawaguchi geometry of order 2 was previously studied by Losik, Lemlin, and recently more by Perzhensky. And yeah, we therefore called it KL square manifold, because these are the special instances of Kawaguchi geometry satisfying this constraint. How much time? Sorry, David.
5 months.
Okay, so as I said, our structure is almost symplectic, and it has this the function which is symmetric. What it gives you, actually, it defines you a connection. So when you have a symplectic structure and a connection on the manifold, you cannot find, unlike in Riemannian case, when you have a connection in the metric structure, you can find unique torsionless connection for a given metric and a symmetric connection, torsionless connection. In a symplectic case, it's the same in almost symplectic. Given a symmetric connection, so torsionless connection, and a symplectic form, there is no unique connection which would be compatible with this symmetric connection. They are always defined up to the symmetric three tensor. So you always have this freedom to define your torsionless connection. For us, obviously, the torsionless connection would never be compatible with the metric, because in our physical problem, we said it's almost symplectic structure. It means there is a torsion there, so symmetric connection will never be compatible, because there is a torsion coming from the actually derivatives of omega. We can, however, any such a connection will define you fully symmetric object, gamma, given like this, and this also will all give you kind of covariantization of this gamma function with this connection coefficient, such that you get this symmetric three tensor, which parameterizes your freedom of finding a connection which are compatible or not compatible with symplectic or almost symplectic structure. Okay. And now in our system, as I said, Kawaguchi geometry, so the action which is reparameterization invariant, including the structure function we have, omegas and gammas, are actually given like this. It's arc length, it's a cubic root. So Kawaguchi geometry in our sense, KL2 action, has a cubic root because this is what makes this reparametrization invariant. You have dt and then you have 3-time derivative here, you need the cubic root. And for omega non-degenerate, you basically can write it like this. You can invert omega here and define acceleration with omega inverse gamma to get this system. And okay, obviously for this audience, I will skip this. We have a cubic root. We know from the previous example that you can always get classically equivalent action without the cubic root, think Nambu-Goto and Polyakov, so you can do it to the standard for a relativistic particle, and then of course also for something we call Kawaguchi particle, you introduce a density of weight 2, Einbein, and you kind of integrate out its algebraic equation of motion. It means you are gauge fixing your parameterization invariance, and when you do this, we claim what you get is the kind of action for the massless Kawaguchi particle, which is exactly our cubic correction to the effective action. So we got a geometric interpretation of these corrections in the third order. And one thing that I still didn't tell you is after this interpretation, the geometric understanding of the cubic action, what is the definition, covariant definition of jerk? So as acceleration, as a second-time derivative of the position is not covariant object in a curved space-time, you have to make it covariant by introducing acceleration and a connection. The same thing, we define the covariant jerk as a covariant derivative of the acceleration, and we allow for the fact that these two connections needn't be the same, because always when you play with a connection, there is always freedom. The things physical things shouldn't depend on the choice of your connection. Basically, you can move the things from the contortion to the non-metricity and stuff like this. So you always have the freedom in choosing connection. So what we did is we chose a particular connection of this form such that our equation of motion in third order for covariant jerk is given like this. So this is the second order. I get a contribution from which looks like symplectic curvature here for this gamma zero connection with jerk here. As I said, there is a freedom of choice. If you choose a different connection, basically what you will do, you will just reintroduce some h moving around here, but this is the freedom you have. So what is this equation? Well, if you had a globally flat connection, what you would get is just kind of equation that mimics free motion. In standard Newtonian motion, you will get jerk-free motion in the in your parameter space. So this is the interpretation. Okay, this is just the summary. I gave you the results at the beginning. So what we learned from the Kawaguchi understanding of our cubic correction of the action in the geometric sense is that we have almost symplectic structure and some symmetric function which induce the connection on our manifold, and then this covariantizes jerk. In analogy, what is kind of left to be done, what we want to do is to do the numerical simulation, because what we want to see is that once you try to solve this equation, how you're hoping that your contribution for the jerk, which is cubic in your adiabatic parameter, will not cancel out in the long time, so that we could obtain something like visible long time effect on the motion of the nuclear due to the integrated quantum effect in the even for the small correction coming from the third order. And I will stop here. Thank you very much.
Very much. We have time for some short questions.
Thanks for the nice talk. And I would like to know, I don't know if you can mention very briefly about this tension, about what you said in the very beginning about computing the equation of motion from the Lagrangian or in an effective way. What is this tension, and if it is possible to include extra geometrical constraints, for example, to make this compatible?
Tensions come from the fact that you're basically doing different approximation on different level. So think consistent truncation. You cannot always do the truncation and the action and the equation of motion and make them match. The terms, so we did it also just from the equation of motion point of view. We got two extra terms which depend on the Berry curvature and the higher version of the Berry curvature. So they come, so think like Riemannian corrections come in the even orders, and the corrections to Berry curvature kind of come in odd orders. And these are special, these come in equation of motion. They are non-Lagrangian. This is kind of expected. And they do not contribute to work. So effectively, you will not see them because they don't do any work. But yeah, they're non-Lagrangian. So we were kind of not playing there. Ryan contacted because he was working or discussing with Michael Berry about he sent our paper. He doesn't like this third time derivative. He said he would prefer everything to be non-Lagrangian. It's fine. But if we could, put the third time derivative in some boundary conditions and special solutions, he would be most happy because he is not treating these slow degrees of freedom in this way. He defined something what he called a slow manifold, which you can do for very special initial conditions, and then all the motion on this slow manifold is Newtonian. All the equations are Newtonian, but then you have very special constraint on the defining what is slow manifold, where you have the motion like this.
Okay. Thank you. In view of time, thank you, Larisa, again.